about rocket engines, right? Yeah. That's great. Take it away.
Make sure this works first. All right. Hello, good afternoon, or should I say good morning, Edison. Good morning, class. My name is Tim Cannon.
Dr. Edison.
And, what?
Dr. Edison.
Dr. Edison.
Dr. Edison.
What's off?
Can we restart, please? From the top. Good morning, Dr. Edison. Good morning, class. My name is Tim Cannon, and this will be my 6-minute talk over rocket engines. Before we get started, I'd like to point out all the different shapes and sizes of these. You can see the Rocket Lab Rutherford engine, Peter Beck's literally holding that compared to Blue Origin's BE4, which could swallow several people, it looks like. And you got the Soviet-made RD-182 bells, 2 SpaceX engines. So in this presentation, I'm going to answer these questions. What is a rocket engine? How do rocket engines work? What's the big bell at the bottom? And what is an aerospike engine versus a traditional bell? And so also, I'm going to kind of blow through a lot of this. It's a lot more complicated. It's going to be oversimplified, but here we go. What is a rocket engine? It's basically an engine that throws mass out the back in order to push your rocket or whatever you're propelling forward. Newton's third law, think about that. You can also think about conservation of momentum, right? You shoot out a massive velocity one way, kind of like the explosion stuff from physics. Then you got to be good. You got the rest of your whatever mass you have has to go the other way. And always remember when it comes to rocket engines and rockets in general, pointy end down, flamey end down. Okay? So how do rocket engines work? Well, the most basic form is a pressure-fed rocket engine. So you have propellant at a high pressure, goes through a valve, and it's blown out the back end at low pressure, right? You have to flow from high pressure to low pressure. Kind of think of a balloon. That's not a rocket engine, but similar idea. You've got high pressure gas, it gets blown out, and then when it goes the other way, right? And then also, just so you know, in here we're going to have a combustion chamber. So we're going to end up setting that on fire, getting more energy, shooting out even faster, all kinds of good stuff. So for these pressure-fed engines, we have a big problem, right? Because you have to flow from high pressure to low pressure, so you want to have a really high pressure over here. When you do that, you have to thicken up your walls a lot. And what that does is it increases your weight drastically, which is terrible for rockets. And it decreases the amount of propellant you can actually have. So you might not even be able to make it into orbit. So how do we get around this? Well, what you do is you can throw the propellant into the combustion chamber with a pump. But in order to pump like such high volumes to such a high pressure, right, on the Raptor engine, I can't remember, I think they get up to near 300 bar, so it's really high pressure, and we got low pressure in this tank, remember, because that's the entire point of using this pump. You gotta have a super, super powerful motor powering your pump. And that's just not really feasible with something like an internal combustion engine or an electric motor. So what we do is we take a really small rocket engine and we blow that exhaust coming out at ridiculously high speeds right at the, well, we use like the exhaust in order to spin the motor, as you can see in this picture over here. So kind of a smart idea, right? So here's different cycles for rocket engines. These are a lot more complicated. I don't have time to go through everything on this slide, but I'll just point out this most basic open cycle, which is what they use in the SpaceX Merlin engine. You got your fuel and your oxidizer being pumped down in the combustion chamber here. And you can see these two little tubes feeding the pre-burner, which is what we call the small rocket engine. Pre-burner blows on this turbine, which powers both the pumps, and it's exhausted, and that amount of fuel is basically wasted. These other cycles do other things about that. You can ask about that later if you want. Pretty interesting stuff. All right, so what's the big bell at the bottom? Well, a lot of people, I think, at least I did, I guess I won't speak for all you, you think, oh man, you go to Space Center Houston or something, you say, man, check out like the engine, it's awesome. But really all you see is the bell. That is absolutely not the engine. That's like pointing at the wheels on a car and saying, oh, like, check out that car, that's so cool. But the wheels obviously aren't actually the car. That's just what you use to transfer the energy into workable thrust from a car into an motion. This part is the actual engine, which we just looked at, all those cycles and everything. So let's take a look at a 2D view to see what's going on. We got a combustion chamber where the fuel and the oxidizer are mixing really, really high temperatures, really, really high pressures. And then, all right, well, I guess also speaking for myself, it doesn't make any sense, right, that our valve, or our nozzle, I should say, so the bell, I should back up here, I got ahead of myself. The bell is just a big nozzle. which speeds up what the mass that you're throwing out the back, right? And so here, right? So I would think, okay, well, if it gets bigger, it's not going to speed it up. I know how nozzles work. I took thermodynamics, right? But you can see here, we actually do. So we get smaller, as you would expect. We're accelerating the exhaust right here. Then we get to the thinnest area, and that's where we reach the local speed of sound of the exhaust. So the speed of sound, it increases as temperature increases. I think with a square temperature, actually, I could be wrong. But if we keep constricting this even more after it's at the local speed of sound, we're just going to choke the flow, and then bad things will happen. So what's going on in the other part of this nozzle, this converging diverging nozzle as they're called, it's a really scary thing that none of us have really learned about called compressible fluids. And I don't really know all the fluid mechanics that go on in there, but I do know that for at least compressible fluids in this case, as the cross-sectional diameter increases, your fluid accelerates. Counterintuitive to what we might think, that this is more like what we're used to, at least for me. But in fact, it does accelerate a lot. Its temperature drops a lot as well, and the pressure. So in these bell nozzles, we start off really, really high pressure, and then the pressure decreases as we go in the X direction along the bell. And so the goal is that at the end here, we want our pressure of the exhaust to be the same as the pressure in all the ambient air, because that means our exhaust can be shooting straight out the back, right? If our exhaust is spraying to the sides or it's going inward, it's not like we're losing efficiency. Again, conservation of momentum, Newton's third law, right? But in reality, since our rockets are changing their altitude constantly, we're never, besides for a split second, going to be at that perfectly optimal operating point. So what happens is you have, it's kind of hard to see, but you have underexpanded and overexpanded bells. So an underexpanded bell means that the ambient pressure is a lot lower than the pressure at the very edge of your bell. So as soon as the exhaust gets outside of that bell, it starts spraying outward. You can kind of see it here. This is a rocket really high in altitude, and its exhaust plume is going every which way. And then you got overexpanded over there. Overexpanded is the exact opposite. So the ambient pressure is higher than the pressure at the end of the bell. It starts constricting the flow in, and you get these really, really pretty shapes here, which are just a sign of inefficiency. This is just a big gnarly shock wave. It's not really good, but they look really cool. And so this is where we come, or this is, I guess, what we have: sea level optimized versus vacuum optimized engines. The engine itself is the exact same. This is the Merlin engine, SpaceX Merlin engine, used to power the Falcon 9, Falcon Heavy. And so the engine part, the pre-burner, combustion chamber, it's all the exact same. Literally the only difference is the size of the bell. Because, as I said, we want to operate where the exit pressure is the same as the ambient. And so the bigger the bell, the lower your exit pressure is. So in a vacuum, theoretically, you'd have to have an infinitely big bell, which isn't practical, obviously. Can't do that. But you just make it essentially as big as you can. And then you have a much smaller one for whenever you're operating at sea level. That's where part of the reason you have different stages in your rocket. It's a lot more complicated than that, but here's an example of the difference. Here is the vacuum optimized Merlin and the Falcon 9. There's only one of them. See, you can see how huge the bell nozzle is in there compared to the 9 Merlins that can fit on the first stage. Again, the exact same engine, just this one has a much, much bigger bell. So you might say, why don't we just use vacuum engines at sea level? We're only at sea level for a split second. So why don't we just do that, and then we don't have to worry about the different stages and all this other craziness that goes on. Well, it's because whenever you have too big of a bell, I can't remember the exact percentage, but whenever the pressure at the exit is too much lower than the ambient pressure starts pushing in, like it constricts the fluid in so much that it starts pulling up into the bell itself. So you get flow separation on these walls, you get all these nasty shock waves, and it shatters your engine. So that's not good, especially not for sending people up. So finally, what's an aerospike engine versus a traditional bell? Well, basically, as you can see in this diagram, it looks very similar to the picture I showed earlier. You just cut half the bell off. And this essentially uses the ambient pressure to push in as the other side of the bell. So this ambient pressure pushes in on your exhaust. You shoot your exhaust along this wall. So essentially, you're always operating at optimal efficiency. You always have your exhaust going straight out the back because you're using the ambient pressure itself to simulate the exit pressure of the bell. It's pretty cool stuff, but they're also not used at all for various reasons. Mostly because, as you can see here, we've got like 20 combustion chambers on this side of this one linear aerospike engine. Cooling one of those is hard enough, much less 20. It's basically impossible unless you increase the size tremendously in the weight, and that's just not practical at that point. You won't be able to get it up into orbit if you've only got like this ginormous engine that carries all your payload weight. Up top, that's another form of aerospike. That's a toroidal aerospike. There's just different forms. But I think that's all I have. Yeah, there's my sources, NASA, SpaceX. And is there any questions? Yeah.
So are the aerospike ones just like, I don't want to say theoretical right now because they obviously are real. But
Yeah.
what do they use them for? Just
Well,
testing?
people. Well, so there's been a few projects where they've wanted to use them, and those projects have failed. I mean, so basically the holy grail of rockets is a single stage to orbit rocket where you don't have to knock off the first stage.
Okay.
Think of Star Wars, that's how I like to think of it. Those are all single stage to orbit, just the one ship goes up and leaves.
Okay.
And so these have been tried to use on some projects for single stage to orbit rockets. There's no, the space shuttle is kind of an odd one, that's like half and half. But they've been built clearly, and they're being tested. They're trying to be able to make them so that you can use them. Like if you could have something that works in all situations, that's what you want to use.
Right.
We're just not able to have it right now.
Okay.
Yeah, that's. Yep.
What happens to the equipment that's shedded off in each stage? Like, you know how generally stuff falls off the rocket as you...
Yes.
So
Well,
what happens to that? Like, is it reused? Does it just land and they throw it away? Or does it just stay on the ground? Like, what happens?
It depends on the rocket or whoever's launching. Right, SpaceX, I think we all know, they catch their rockets. Blue Origin, they're also building, and they have built reusable rockets. Rocket Lab's working on it too. So it really just depends. Some of them, they knock it off and then it burns up in the atmosphere. They drop them over the ocean so that you don't land on any people, right? And then a lot of times we go retrieve the debris, but you can't reuse it. So it really depends. Like the space shuttle, a lot of older rockets, you can reuse any of it. A lot of the engines can be either refurbished or reused nowadays. The RS-25s are able to be refurbished now, which is what they use on the space shuttle and the upcoming SLS. There's also different ways to do it. SpaceX does propulsive reentry. So they fire up the engines again to slow it down so that the first stage doesn't burn up and they can reuse it. Rocket Lab, they use this little parachute and then a bigger one. They catch it with a helicopter. Theoretically, they're still working on it. And then also Rocket Lab, like there's obviously different equipment, as you said, that falls off. Rocket Lab, they don't use pre-burner turbo pumps. They use battery-powered ones because their engines are so small. So they actually knock the batteries off and those burn up. They have to do it as they go, or else they won't make it into orbit because the tolerances are so different.
Rocket Lab is a space company, like SpaceX?
I mean, it's a different company that builds rockets. They do, their rockets are a lot smaller. They do like private launches, so like kind of, so anyone can send something up theoretically, or companies that have smaller satellites and stuff.
But they're private though, right?
Yeah, they're private.
And then have they actually got rockets in space then?
Oh yeah, they do. I think they've only had one. I can't remember exactly. As of like last year, they were 100% like on their success of their missions.
So they just send things into space?
Yeah, basically.
Like
Someone pays them like, hey, I want this satellite up there, and then they launch it.